Dear students, welcome to the lecture series on the topic engineering graphics. So today we are going to discuss about the projections of the oblique planes. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. So an oblique plane is the one which is inclined to both the reference planes, that is horizontal plane as well as the vertical plane. So let us first of all read out the statement to evaluate the order of inclination of this oblique plane with respect to the two reference planes, that is HP and VP. So there is a thin circular lamina having diameter equal to 50 millimeter which is resting on horizontal plane such that the lamina is inclined at an angle of 30 degree to the horizontal plane. So this means that the first inclination of this lamina is available with us with the horizontal plane. So the lamina is first inclined to the horizontal plane and then it is inclined with the vertical plane. So the second inclination of this lamina is available with the vertical plane. So to begin with, we are going to assume that this circular lamina is contained by the horizontal plane. So its true shape, that is the circular form, will be obtained onto the horizontal plane in the top view. So the top view of this lamina will be drawn below the XY line measuring 50 millimeter. And once we are looking at this lamina in the front view, so since this lamina is lying onto the horizontal plane, so its front view will be obtained in the form of the edge view drawn onto the XY line. It will be coinciding with the XY line. Now we are provided with the second inclination, that is the plan of the diameter is inclined at 45 degree to the vertical plane. So it means that angle beta. So what is angle beta? So angle beta is the angle of inclination of the apparent length, that is plan of the diameter of the circular lamina with respect to the vertical plane. Then the second case suggests that not the plan of the diameter but the original diameter is inclined at an angle of 45 degree to the vertical plane. It means that we have been provided in the second instance the angle phi over here. So angle phi, which is the angle of inclination of the true length of the diameter with respect to the vertical plane. But since in the case number 4 we will be able to work out the projected shape of this particular lamina in the top view, so we have to determine angle beta from the given angle of angle phi. So we will be making use of the principles of the rotation of the line to evaluate angle beta starting with this angle phi, and once this angle beta is evaluated, then we will be able to draw the projections of this oblique lamina. Now in this case you can see, since we have to draw a circle, so there is no problem regarding orientation of this circular lamina. So straight away you can draw a circle in the top view, but in this case you can divide the circle into 12 or 8 equal parts so that whatever elliptical figure will be available in the front as well as in the top view, so you are able to get an appropriate elliptical figure constructed into the front as well as the top views. So it is better you divide circle into 12 equal parts in order to have more number of guiding points to be able to draw an elliptical figure appropriately. Now let us start with the projections. So first projection will be that of the true shape. That is, first of all we are going to assume that the lamina is not inclined to the horizontal plane. So we are going to assume that the lamina will be contained by the horizontal plane. Why? Because the first inclination is with respect to the horizontal plane. So first of all we are going to draw the circular lamina, and as I told you that we have to divide this into 12 equal parts. 12 equal part means that angles of 30 degree each you should draw on this side. So automatically once you extend those angular constructions that you have made, so you will be able to divide this circle into 12 equal parts. So just see, we have divided this circle into 12 equal parts, and all these subsections, they will be equal because each sector is having included angle of 30 degree. So once we have drawn the circular lamina true shape onto the horizontal plane in the top view, so we have obtained the true shape of this circular lamina. Now let us draw the front view. In order to draw the front view, the projectors through all these points, 12 points, onto the horizontal plane, that is XY line, have to be drawn. So just see, we have drawn projectors through all these 12 points, and we have been able to locate all these 12 points in the front view. So you just see, point 1 is projected over here as 1 dash, 2 and 12, they have been projected over here as 2 dash and 12 dash. Similarly, 3 and 11, they have been projected onto XY line as 3 dash and 11 dash. Similarly, 4 and 10 points, they have been projected onto the XY line as 4 dash and 10 dash. Similarly, points 5 dash and 9 dash have been obtained, and 6 dash and 8 dash and 7 dash have been obtained. So having obtained this edge view, now the next task is to incline this edge view, that is the surface of the lamina is inclined at an angle of 30 degree to the horizontal plane. Now all these points, you see, I am going to mark this length from starting from 1 dash up to 7 dash. So whatever edge view is obtained in the front view, because my lamina was lying onto the XY line, that is the horizontal plane, now this projections, all these projections of 12 points will be translated or rotated with respect to the horizontal plane at an angle of 30 degree. You see, we have drawn all these dots, that is from 1, put a dot over here corresponding to 2 dash and 12 dash, again put second mark or dot at 11 dash and 3 dash, and similarly mark another dot at 10 dash and 4 dash, and mark another point at 9 dash and 5 dash over here. Similarly mark another point corresponding to this distance, 8 dash and 6 dash, and finally 7 dash is drawn. So once we have drawn all these points at an angle of 30 degree, that is edge view has been transferred or translated or rotated at an angle of 30 degree. Now from all these 12 points we are going to drop vertical perpendicular projections, and from all these plan projector points we are going to draw horizontal projectors which will be intersecting these vertical projectors at different points. So the common point of intersections we need to work out, just like you see, this is point 1 1 dash, this is point 1. So this intersection gives us the location of point 1 1. Similarly, this is the projector for point 2 and 6. So point 2 will be lying over here. So we are going to get projector of 2 point onto this line. Similarly, point 3 will be projected here, point 4 will be projected here, point 5 will be projected here, point 6 1 will be projected here, point 7 1 will be projected here, point 8 1, 9 1, 10 1, 11 1 and 12 1, all these points will be projected here. So once we project all these points, you can see this is 1 1, again 2 1, 12 1, 3 1, 11 1, 4 1, 10 1, 5 1, 9 1, 6 1, 8 1 and 7 1 have been projected onto the plan view. And here we obtain this ellipse. So this ellipse we have to draw freehand. So this ellipse we are going to draw freehand, and this gives us the projection of the circular lamina once this lamina is inclined with respect to horizontal plane with respect to any given angle. So here you have 30 degree over here. Now you see in the next case, that is the plan of the diameter is inclined at an angle of 45 degree to VP. So this is the original length of the diameter. Please check this out. This is 50 millimeter. So this is also 50 millimeter. This is the diameter of the lamina, and this is again 50 millimeter. So 1 7 is 50 millimeter, 1 dash 7 dash is 50 millimeter, 1 1 dash and 7 1 dash is also 50 millimeter. So this is the original length or the true length of this diameter of the lamina. But while you incline this surface of the lamina at any particular angle with respect to the horizontal plane, the projection of the diameter, that is 1 dash and 7 dash, as it is projected in the top view, this will be reduced 1. So here we obtain 1171 as the plan or the apparent length of the diameter 17. So corresponding to 17 diameter, in the plan the length of the diameter will be reduced. So that is why we have said that 1171 happens to be the apparent length. Now we are provided with second set of instructions, that is the plan of the diameter is inclined at an angle of 45 degree with respect to the vertical plane. Now over here, so with respect to the vertical plane, now 45 degree angle we are required to draw. So just see, we have drawn a reference line and 45 degree angle we have drawn over here. So this is the angle beta, which is equal to 45. But what do we mean by angle beta? Angle beta is the angle of inclination of the reduced length or the apparent length or the plan of the diameter with respect to the vertical plane. So we have to now shift, please see, we have to shift this figure of the plan over here at an angle of 45, because fifth figure that we are drawing in projection of plane, it is again rotation. So figure 1 is the true length, figure 2 is the edge view, figure 3 is the rotation of the edge view, figure 4 is the corresponding figure, figure 5 is again the rotation, and figure 6 will be again the corresponding figure. So here I need to translate all these points, I need to rotate all these points in such a way that 1 7 will lie here, 1 2 and 7 2 will lie here, and all the other points I have to locate appropriately. So let us see how we can once again go about shifting this figure over here so that 1 7 diagonal will be located along 45 degree angle with respect to the vertical plane. And mind you, just like what we did in the previous cases, we are going to mark rectilinear distances over here. How? Please see, I'll mark point 1, point 2, point 3, point 4, point 5, point 6 and point 7. So all these points 1 to 7 will be marked along this diameter 1 7. So this is my apparent length of the diameter. Onto this apparent length I am going to mark all these 7 points. 1, 2, 3, 4, 5, 6 and 7. Having marked these 7 points, first point the vertical distance is 0, seventh point the vertical distance is 0. Corresponding to the second and the sixth point, so this is my vertical distance. I'll measure only one distance, so distance of 12 from this point and distance of 2 is equal. This is equal to distance of 0.8 and distance of 0.6. So from points 2 and 0.6 I'll mark this distance 4 times and I'll obtain 4 points of this elliptical surface. Similarly, from points 3 and points 5 I will be measuring this length, which will give me distances of the point 11, point 3, point 5 and point 9. Again one distance is measured, but I'll be getting 4 points over here. Similarly, corresponding to the point 4 I'll be measuring this length and this length. So this is nothing but this is 25, this is again 25. So corresponding to all these 7 points, the vertical distances will be measured for all the points of the ellipse, and these will be projected over here. So just see, this is my apparent length 1 7. Now which is same length which I had obtained over here. Onto this length 7 points they are going to be marked, and now this is the rectangle which is going to cover my circular portion. So my ellipse will be inscribed by this particular rectangular portion. Now here you see, here we go, 7 points we have marked over here, and corresponding to these 7 points Now the vertical distances we have marked as I have told you just before, and once you mark all these points, just see from point 1 and point 7 vertical distances are 0. From point 1, point 2 and point 6 measure just one distance. The moment you measure only one distance, this will give you location of point 12, point 2 over here. Similarly, location of point 8 and point 6 will be obtained. From points 3 and 5, just measure one distance, because this distance is equal to this distance, which is same as distance of 5 and 9. So from here, same distance will be projected vertically, that is rectilinear distance, and 4 points will be obtained. From point number 4, again measure this distance up to 10 and up to 4. And once you measure those distances, so all the 12 points, they are available with you. And once you have all the 12 points available with you, once again join this ellipse freehand. So once you are joining this ellipse, we are able to successfully rotate this figure at an angle of 45 degree. That is, the plan of the diameter is inclined at an angle of 45 degree with respect to the vertical plane. Now I will be taking off this rectangle. I will be taking off these artificial construction lines which are required to locate all these points. So now I am going to take them off just to simplify the things. Now the top view has been obtained. Having obtained the top view, now the front view needs to be located. So the same procedure will be followed. From all these 12 points, I am going to draw the vertical projectors, and from these 12 points of the elevation, the horizontal locus lines will, or the projectors will be drawn, and we'll work out the intersections of the points which are coming from the vertical, from this plan, and the points with the projection lines which are coming through these elevation points. So just see, these are the vertical projector lines which we have drawn through all these 12 points, and these are the horizontal projector lines which we have drawn from the elevation view. And we are going to find out the points of intersection of the corresponding points over here. And once we locate all these points, just see point 1, 2, 3 and all these points, they will be located. And once the corresponding points of intersection, they are located in the front view, now I am going to join all these 12 points, and this is going to lead to generation of an ellipse over here, because this was an ellipse which is inclined to both the HP and VP. That is, the lamina is inclined to both HP and VP over here. So that is why there is serious reduction in the shape over here. So this is the apparent shape of a circular lamina which happens to be inclined to both the horizontal plane and the vertical plane. Now we want to proceed with the second case, that is, the diameter is inclined with respect to VP at an angle of 45 degree. Now here we have not said that the plan of the diameter is inclined. It is true length of the diameter which is inclined at an angle of 45 degree. But please note that over here, whether it is the original diameter which is inclined or it is the plan of the diameter which is inclined, ultimately we are required to transfer or rotate this figure onto this particular place. Only difference between this case and this case is, here angle phi is given. From angle phi, using the principles of rotation of line, we are going to work out this angle beta, and we already know that apparent angles, they are always greater than the true angle. So since here the true angle is given to us as 45 degree, so from this we are going to work out angle beta, and angle beta will be greater than 45 degree. This we already remember from the projections of the line. But to begin with, what we have to do, once again a construction line we have drawn over here. We have marked an angle phi. Please see, angle phi is equal to 45 degree has been marked. Now since angle phi has been marked to be 45 degree, I cannot draw this apparent length over here. I need to draw true length over here. What is the true length? I have already told you 1 7 is the true length, which is equal to 50 millimeter. 1 dash 7 dash is also the true length, which is 50 millimeter. So I have to mark 50 millimeter length along this 45-degree angle. Now please check. I know that this angle phi is equal to 45 degree. So along this line I have to draw 45 degree and 50 millimeter. So the names of these 2 points will be A, B1. So here what are these two points? The 2 points are 1, 1 and 7, 1. But these points, they are the apparent lengths. Now my starting point will be 1, 2 over here, just like it is there 1, 2. But this point will not be 1, 2. This point will be 7, 2, 1. Because true length is always supplemented by one more character over here. So one more numeral is added. So you see, I am going to mark this length as 50. Earlier on, I had marked this length to be lesser than 50, which is the apparent length of the plan over there. That is 1, 7 plan, or the reduced length is this one. So earlier I had marked this because the angle beta was given. So beta was the angle of plan of the diameter being inclined at an angle of 45 degree to VP. But here I am provided with the angle phi. So angle phi is the angle which the true length of a line, so which the true length of the diameter of the circular lamina makes with the vertical plane. So angle phi is equal to 45 degree. This length AB1 is equal to 50 mm. So this point is 1, 2 as it is shown over here. This point's name will be 7, 2, 1. So this is the true length. So true length of this lamina is inclined at an angle of 45 degree with respect to VP. But I cannot transfer this figure over here because here I have got only the plan of the lamina. So ultimately I have to work out the angle of inclination of the plan of the diameter with respect to my vertical plane. That is, I want to evaluate the angle beta over here. You see, angle beta is the angle of inclination of AB with respect to the vertical plane. But here I have got the line which is the true length. So true length is equal to 50 millimeter. This I know. So since angle phi was given to me, so I have drawn 50 millimeter length inclined at an angle of 45 degree. So this is the true length of the diameter. Now what I know from the rotation of the line principle, that is the locus lines of first point and the second point, they are the same whether you are drawing the true length or whether you are drawing the apparent length. So I know the true length, I have drawn it. I know the angle phi, I have drawn the angle phi. Now I also know the apparent length. You see, apparent length of the plan of the diameter is also known to me. So what I am going to do now, I will use my compass or my divider to mark this length, that is the apparent length of the diameter of the circular lamina. So I'll keep my needle here, my pencil will be here, and I'll open the compass this much and cut an arc corresponding to the apparent length of the plan of the diameter, because ultimately it is only this figure which is to be transferred. So I have to work out the angle beta which is corresponding to the apparent length of the plan of the diameter. So using principles of the rotation of the line, I know these two projectors will remain same. So I have drawn the true length, I have drawn the true length, I have marked the angle phi, I have marked the angle phi. So between these two locus lines, now since I know this apparent length, I am going to mark this apparent length between these two locus lines. So just see, I have marked the locus line over here. So this is the apparent length which was available to me in this top view. So by drawing this apparent length between these two locus lines, you can see these are the two locus lines and this is true length. So between the same locus lines, my apparent length will also lie. So it means that point B, so which is point B? Point B is my 7, 2. So this point has been located. Just see, I have marked an arc over here. So having marked an arc, I know my angle beta, and now you can very well check this angle beta is greater than angle 45. So once you measure this, you will find that this angle beta will appear to be approximately 50 to 51 degree. So this angle of inclination will vary, it will increase. And once you know the angle of inclination of this apparent length, now there is no problem. I can once again use the same principles, that I will have to put this entire figure, I will have to translate or rotate this entire figure with respect to this apparent length. So once again, just like we had marked all these 12 points over here at an angle of 45 degree before, now this angle has changed because angle phi was 45 and this angle beta now we have evaluated equal to approximately 51 degree. So only the angle of inclination has changed. Now having located this angle of inclination as 51 degree, that is beta, so same figure as obtained in case number 4, this will be rotated or translated not with respect to this true length but with respect to this apparent length. So I have translated this figure. So having translated or rotated this figure over here, now my projections of the lamina in the top view have been obtained when the diameter was inclined at an angle of 45 degree to the vertical plane. And finally, the front view has to be obtained. So once again, the same procedure for all the 12 points, we'll take the vertical projectors upwards. For all these 12 points from the previous elevation view, all the 12 points horizontal locus lines will be drawn and the corresponding points of intersection will be evaluated. Just see, this is point 12 dash, 12 dash, one by one we have evaluated all these points. And now you can see, after evaluating all these points, now we have joined all these points with the help of a freehand curve and the final shape will be that of an ellipse. Now you can see only difference between this case and this case is the angle beta. Here angle beta was given, so here angle phi is given and the beta has been evaluated. So here beta angle is 51 degree, here beta angle was 45. So since the angles are different, you can see that minor changes in the shape of the ellipse have been obtained. Otherwise, rest of the procedure remains same. So in the final case, since the angle phi was given, so angle beta had to be evaluated. So that is an additional step which is required in this particular case. So rest everything remains the same. So with this, we have worked out how we can draw the front view as well as the top view of the circular lamina when the lamina happens to be inclined to both the horizontal plane as well as the vertical plane. So this is all about the projections of the lamina, that is circular lamina which is inclined to both HP and VP. So we'll continue with the discussion regarding projections of the oblique lamina in the subsequent lectures as well. So I hope you have understood how you can go about constructing the front view and the top view projections of the oblique circular lamina. Thank you very much. Thanks a lot. Thank you.